Okay, today we like to cover the subject of hydrogen storage as a continuation of hydrogen pipeline distribution system. Let's quickly take a look at our lecture note. In content, chapter 4, we discuss about the hydrogen distribution systems, mainly pipeline, and there are other methods such as trucks and ships, and compression and liquefactions, and safety and etc. and pipeline blending. So main point here is the pipeline. Pipeline is a very efficient method to distribute hydrogen gas. The gas can be generated from different technologies. One of a very typical method is the green hydrogen using the electrolyzer, the method called electrolysis. So once we generate hydrogen, we distribute through a pipeline. So let's go to the last homework. Okay, let's go to our homework. Okay. This was the homework number 3, design of a hydrogen piped. Let's copy this into our lecture note here. Okay, this can be one of a very typical problem you may face when you when you work on some designing of the pipes and other stuff. You would have this kind of questions. Okay, let's imagine we as an engineer need to solve these kind of problems. Design of hydrogen pipes. Well, select the best data leading to a lightweight pipe, thinnest thickness, and now what will be the thinnest thickness? ID, internal diameter, is the 100 millimeter, and maximum inner pressure will be 70 bar times 4 equal 280 bar, and maximum strain should be less than 2%. Layer thickness and angle ply laminate, n times of a plus minus theta, and use glass PE as a comparative winding. Well, if you don't know anything about the pipeline or glass PE or the angle ply laminate, I'm sure at the very beginning you would not have any kind of experience on these types of problems. So let's just go to ChatGPT and then see what they say. In this dialog window, I just copied it. Select the best data and etc. and then enter. Now the command of select. We are telling ChatGPT to select this best theta and see what they are saying. To find the best theta, winding angle, proximate theta for a lightweight composite pipe. See here, okay, made of a glass PE. Now you know what is a glass, what is a PE. PE is glass fiber reinforced polyethylene. Polyethylene is the thermoplastic. That means the pressure and strain requirement. And we will follow this engineering approach. Now, problem summary is important to redefine or clearly understand the problem. Inner diameter and maximum inner pressure, well, bar and megapascal is 10 times of the megapascal is a bar. And strain limit, it says a hoop, but we didn't say anything about the hoop here, right? But they understood strain limit in a hoop. You understand? I didn't say anything about the hoop, but it says the less than 2%. And the material system, this and layup, angle ply laminate, repeated approximate beta, and goal, minimize the wall thickness. Now there is some, I hate to say this, but the ChatGPT, their answer is not always correct. So you need to double check, you need to reconfirm, or you need to ask in a different way. Let's say, okay, let's quickly review design constraints. There is some formula and the hoop directions and the axial stress, and it says closed end where P and this and this. Now the point is the T, wall thickness is not given yet. If we knew T thickness, we would know the stress. Now composite property, we have to know the properties. So we assume that we can assume, but this is a very typical material property of the glass PE. E1, E2. What is the E1? Well, fiber direction. You may not know what is a fiber direction. You may not know what is a transverse direction. If those who already took the class of composite, I'm sure you know what they mean, but let's assume you don't know. You didn't take any class. You don't have any knowledge about the composite. Then I'm sure this terminology may not be maybe new to you. And G1, 2, and mu Poisson's ratio 0.25. Ultimate strain limit, fiber direction. Now they are changing the fiber directions. See, they changed the hook direction and they changed the fiber direction. Fiber volume fraction, oh, sorry, okay. This is a material property they are assuming. Ultimate strain limit in fiber direction. Fiber volume fraction will be 55%. Effect of approximate beta on strength. The strength contribution of each ply depends on the angle, of course. Beta at 0 degree, hoop direction, maximize the hoop stress resistance, plus minus 45, 90, axial, and some of the terminology is not 100% correct here, but let's try to understand what they are saying. The optimized for the burst pressure, plus minus 55 to a 65 is commonly used in pressure vessel, according to DNVGL and ASME pressure vessel design standard for composite. Then we may need to know why this plus minus 55 and 65 is commonly used. The best angle range, plus minus 55, provide a good balance between the hoop and the axial load sharing while maximizing burst resistance and minimizing thickness. Estimate minimum thickness. This is the key point. We assume classical laminate theory to estimate strength for simplified, and we estimate allowable effective stress of 55, and like this. Well, this is a quite unknown value. Why they provide, we don't know yet. And using this 600, we put it here, and then we calculate, they calculate the T, PR divided by this, and then 2.33 millimeters. Okay, so final result. This is the formula to calculate the T when theta equal plus minus 55. So 55, 2.3, and the 60, 2.5, and etc. And as you can see that when angle is the 55 is 2.3, and this gives us the thinnest thickness. So we can see that this is the best one. Recommendation, best angle, and etc. But if we don't know anything, then we may ask, what if the winding angle is 45 or 50? Well, great questions. The reason is that, the 55 and this is increasing. We need to confirm what if we angle is less than 55, and let's evaluate what happens when the winding theta is 55 instead of the 55 instead of 50 instead of 55. Okay. And there are some procedures and etc. And the thickness estimation is a 2.3. 55 was a 2.3. Now, if the angle is a 50, the 2.5, the thickness getting increased again. So this is a thicker than when theta is a 55. So they added this 50 as a 55, 2.5 and 3.2 and 2.3 and etc. So you can see that 55 is the give us the thinnest thickness. Okay. Now, I'm sure most time whenever you communicate with the ChatGPT, you would have this kind of answer. They directly give you some final result without a full understanding of the procedures. Well, we can just blindly use their result, but that's not recommended. You may need to know why this result. We should understand that one thing for sure, this procedure, what is missing here? What condition has been missed in these procedures? Well, they didn't consider anything about the maximum strain less than 2%. So I would say, how about maximum strain less than 2%? Did you consider this design? Well, it says excellent follow-up. Yes, let's now explicitly incorporate the maximum allowable strain, less than 2%, into analysis. So we would know that the internal hoop strain, they keep saying hoop strain, and then hoop strain, there could be some effective stiffness, and so input value, put it here. Well, we don't know how these they get these equations, but let's buy that right now. So put all the values. I mean, these values are from assumed material property, actually, which is a very common material property, as shown here. So input value this and estimation of 50 and et cetera. And the so hoop directional stiffness and the strain is 5.2%. So this violates the 2% strain limit. How to fix it? Well, we need to increase the wall thickness to reduce the stress. See, if you just follow this direction, the answer is wrong. The point is that ChatGPT follows the procedures of, from the website and very common procedures. They missed this strain constraint. Please consider strain limit and recalculate the minimum thickness. Well, as you can see, they didn't consider the strain limit and then calculate the strain. It give us a 5%, 5.2%, which is much higher than 2%. So we are asking them to recalculate. So strain limit, composite pipe thickness, angle, and so on, and etc. Here is the restricted minimum wall thickness required for this 2% strain limit. Let me know you would like to extend this more angle and this. See, this is quite wrong directions. It says what they did is just a changing angle, okay? Changing angle and then calculate minimum thickness. This is not quite right. I kind of noticed that, okay, since the that angle is 55 degree, oh my God. We have to increase the thickness uh, until the maximum strain reaches. Let's keep using 55, and then let's increase the thickness until the maximum. The procedure has to be this way. The best angle 55, no matter what the angle, what thickness, 55 is always the best. So we have to keep the 55, and then we have to increase the thickness until 2% for winding and effective and so on. Okay. Oh yeah. Okay. Now, let me see. So he recalculates 7.85. Okay, this is a 7 point. Okay, I misunderstood. Sorry. The strain limit. This is the older result, which meet the strain limit of 2%. Then 55 is a 7.85 millimeter. Then the thickness, the strain will be the 2%. But very strangely, if the angle is less than 55, the thickness is thinner. The reason is that they didn't consider uh, they calculate the only hoop directional strain, which is not a design specification. All directions means not only hoop but also axial direction. Let's see what is there. So using this one and then calculate the strain, 1, 2, and shear strain, and get the principal strain. Principal strain giving us always the maximum. This is the procedures we have to go through. And then when consider all directional strain using a winding angle 55, now the minimum thickness it should be 10.25 millimeter. And then the maximum strain now is the 1.99. And winding angle is plus minus 55. Okay. So our see, my point here is that when you use the ChatGPT to get the value or to design some, of course, it's a preliminary design, not the final design, but you should keep communicating with the ChatGPT to make sure they fully follow the all the constraints you specify. Again, you don't just copy the answer blindly. You have to double check. ChatGPT may miss some point, uh, and then you keep asking them to correct themselves until they all the answer can get fully uh, meet all the requirements. Then I'm sure that ChatGPT will give you the right answer. Otherwise, uh, you may be very much misled by this ChatGPT. Now, 2% and all kinds. Uh, let's plot the minimum thickness versus the winding angle. Okay, winding angles. Uh, winding angle minimum thickness. The point here is that what if we don't follow the 55? What will be the minimum thickness? Of course, all the result should meet the maximum principal strain 1.2%. So next question is that please recalculate and plot the minimum thickness versus the winding angle rather than 55. Okay. Here is the plot showing how the minimum required thickness varies with the winding angle. Um, you may wonder, 55 doesn't give us the best uh, result, meaning not the minimum thickness, other than the other angles. Well, as explained here, the 55 structurally efficient. Structurally efficient means that there is some theory, failure theory, requires more thickness due to a shear and transverse strain component. So if we consider strain component, then we can get this different result. Okay, we can buy this. Um, the result, this is not quite a practical result. The reason is that originally the problem we specify Oops. The problem we specify at the very beginning. This is the one condition is not quite practical and physically makes sense. That's why we have these types of result. Anyhow, the procedure, as you can see that you can communicate to ChatGPT to reach certain results, and then you can get the more additional results by communication and understanding. Okay, this is one of the review I just like to make. Well, I'm sure that all of the your result won't be the same as the what I get from a ChatGPT. Well, that's not the main point. You may assume different value. You may use a different approach. The value may not be the same. So, but you need to have some logical steps and follow. You may have to have your own reasoning and understanding as well. So, anyhow, okay, let's take the 10 minutes break and then go to a storage system. Okay, see you in 10 minutes. It is 4:25. Let's get back to 4:35. Thank you. Okay, I'd like to redefine our problem of a pipeline and together with the angle ply. What is the angle ply? What is a winding? And what is a hook and axial? And what is a plus minus 55? I'm sure you can. You don't have much experience about the fiber reinforced plastic and etc. Then you would always try to use the ChatGPT or a Gemini website. You need to you should keep communicating until you fully understand. All the procedure we have done here, if you don't know anything about the composite, I'm sure you would have some problems in understanding the procedures, even the results. So you can keep asking, explain about the angle ply laminate. Angle ply laminate is important. What is an angle ply laminate? It's plus minus theta. What is a plus minus theta? And so you should understand this pressure vessel and pipe, internal pressure, induced hoof and axial stress, and all kinds of theory. But the key point is the angle ply laminate. How to fabricate the angle ply laminate. So uh, see, to achieve the angle ply laminate, of course, you can use a hand layup, filament winding, automatic tape placement, or tape layering, or hot press molding. Uh, Sometimes a link is not available. So you can see that this is the fiber, okay? This is all fiber, and this is the fiber tensioner, and this is a resin base, and the roller, and this is the machine back and forth, so that the pipe or tank will be fabricated like this. So eventually this fiber with the resin and there will be some plus and minus. So this is the one very typical procedures of to achieve laminate. And sometimes you use the other method, but let's get back to this is the procedure to achieve the laminate, angle ply laminate. Again, the reason we are going into more detail about this pipe is that these procedures and the design the manufacturing can be extended to storage system. So angle ply laminate. Let's say this is let's consider this is a pipe, and take a look at the this area. Then through the thickness. Oops, sorry, am I sharing? Hmm. Okay, recording and sharing. So sharing is okay. I don't see any box. Okay, so if we magnify this things like this, Usually this axis is the 0 degree, and this is the 90 degree, and this is the 90 degree. This is a hoop direction, and this is the axial direction. So this will be some cross layers, okay. At the bottom, we will have a minus. So that's why we call this one as the cross theta and minus theta. So this one, we go back and forth, and cover the one layer, and then I keep winding, and another layer, another layer. So that's why we can say this is a plus minus theta, and many, many layers. This is the composite type. You may wonder why this type of fiber type composite. Well, there are a lot of the advantages. You can easily find the feature of the fiber reinforced the composite pipe and tank through ChatGPT. But anyhow, this is the one. Now, the main point here is that the strain, let's say, this is the pipe under, okay, oops, internal pressure. Internal pressure giving us again, this one will be subject to axial load and hoop directional load. This is a very well-known formula. And ChatGPT says this is the axial, and this is a hoop. So hoop is the pressure. Pressure is the inside the pressure, okay? Inside the pressure. And actually, this will is not open. When we consider pipe or tank, they always end. It needs to be considered as a closed. Okay. So anyhow, the hoop directional stress is the always the R. R is the radius T, and the axial is the is half of this. So this one is always a true regardless of a laminate. Okay, regardless of a theta, these stresses have to be applied here and there. Now the strain we just mentioned was that let's assume the strain distribution of this. There can be some strain here, here, or here, here. Any direction there can be some strain, right? So I will like just to make a circle here. So this is a circle representing a strain in this direction, in this direction, in this direction, every direction. This can be a maximum strain. What does it mean? Well, this may have a distribution, something like that. Then maximum strain will be this. And this can be any shape. any shape of the strain in any direction. Maximum means the maximum strain in every direction. So this is the Emax. And problem says, let's assume this Emax is less than 2%. Why 2%? Why maximum strain? Well, this is the can be one failure theory, not always true, but the one of the failure theory. So we may not consider this one. Okay. Let's get back to the design of a pipe. Let's forget about the maximum strain, and then recalculate minimum thickness versus the winding angle. See, we have a special restriction as the maximum strain should be less than 2%, but let's try to forget that. And then see what will be the angle, minimum thickness. Well, I don't fully follow this one. The mass versus pressure. Okay, sorry. So fiber ultimate strength. Because we have to consider the strengths of the composite. Those are quite, these values are missed. This result is not right. Let me see. They just use the, well, okay, theta There's a lot of what has been missing here. Now, of course, let's use the Sayu failure criterion to design the pipe or calculate the minimum thickness. See, one of the points is that if you follow, we direct the ChatGPT to come to results, you need to always double check the result. They often give a result with their assumptions, but they don't fully explain the what the hell is this? While the result getting worse. While I asked them to recheck the results. The best angle should be 55, which give us the minimum thickness among all angles. Oh my God. While all the procedure you are watching right now between me and ChatGPT, I hope that you would get some idea, or I'm sure you will have a similar situations. Hmm. Hello.
I'm sorry, but I'm having trouble responding right now. Please wait a bit.
Hello. Hello. Maybe it doesn't.
I'm sorry, I'm having trouble responding right
now. Maybe it doesn't work. Uh, since we are using a Zoom microphone is for the Zoom. Hmm. Okay, this can be still a very good exercise for us to design a pipe. The angle should be around 55, meaning that we should have a minimum thickness uh, when the fiber angle is 55. There is a reason for that. I will briefly explain why 55 is better than any other angles. So we have a laminate here and giving us the plus and minus. Okay, and this is the load, axial load is the half T R and P, and this is the hoop T R or P. Now, as you can see, this is a half of this, meaning that this one is this angle, the magnitude is twice bigger than this axial load. Okay, just imagine that this load is twice bigger than this. Now we are trying to design this angle. With respect to 45 degree, this is just a rough idea, rough conceptual understanding. And the if this angle, okay, this is a theta. Let's try to plot. Here is the 90 degree. Here is the 0 degree. 90 degree means that this layup will be like this, and the 0 degree will be layup will be like this, and 45 will be a layup like this. Now, since this ratio is a 2-to-1 ratio, the load will be higher than this. So the load fiber direction should be more toward this direction, right? More toward this direction, because again, this is a twice bigger than this. So if this is a 1-to-1 ratio, then 45 will kind of giving us the best. The restriction is that there is a plus minus theta. This is the layup constraint. If this load and this load is the same, plus minus 45 will be the best. Best means that all balanced, and then the fiber will effectively carry the load. But again, this case is the 2-to-1 ratio. The angle, the fiber will be more likely toward the hook direction. That's why we are reaching the 55. Of course, to reach this precise number, we have to consider the SIO failure criterion and etc. So Uh, there is a kind of a simple procedures. Let's say we have a fiber like this, and this is a load we apply. So let's consider this fiber, okay? The main point here, main point of design here is the fiber will carry the all the load, not the matrix direction. So this is the fiber, okay? Now this is a fiber, okay, plus minus. This is a theta. If we design so that this fiber carries, only fiber carries the load, then we can transform this load here and this load here. Carry just this decompose this fiber. So this is the axial and the sigma fiber times the cosine theta. And why cosine theta? Well, this is a tensor. So that's why we need a cosine scale. And this is a hoop and the sigma fiber times the sine scale. If we have a other stress in addition to fiber, there would be another term. But we assume that only fiber carries the load. Then axial load and hoop directional load, we have this much, this kind of decomposition. Now the point here is that sigma A and sigma H, this is the 2-to-1 ratio because the sigma H is giving us that as you R over P and H, and this one is a half, right? So this is always a 2-to-1 ratio. If we divide by them, sigma H, then we divide this one disappear, and this will be the sine and the cosine, right? Okay. So this is the what tangent. Uh, this is a tangent scale to. So when this angle, we would have a stress only carried by the fiber, which is the ideal case, according to and then the hoop direction and axial direction, we have a stress given like that. So tangent scale theta 2, what will be the angle? What will be the angle? Angle will be the 55 degree. Okay, so this is a very simple approach to get the 55. Well, we can find out how dummy the ChatGPT can be. But anyhow, nevertheless, we can full use of the ChatGPT in other applications. Anyhow, oops. I'm sorry, I use a different. Oops, very sorry, not here. Oh, hmm? Okay. Now, the topic we'd like to cover today is the storages. Well, last week we understood that the pipeline can be considered as the energy storage system because the pipe itself has a lot of huge internal volume with the pressure, so we can store, compress the hydrogen gas inside the pipe. So that can be also used the energy storage system. You know, understanding energy storage system is very critical in these days. Um, well, I don't want to go in detail, but say this is the temperature versus the density of hydrogen gas. We uh, studied and reviewed this diagram a lot, but uh, I hope that we should be able to visualize and remember. We can draw ourselves with a full understanding. So again, is very important. Again, the density. Of course, the density, the higher is the better, meaning that we can store more uh, hydrogen per given the volume. So the higher the better. As you can see that temperature, the lower the better, lower the better is a trend for the given pressure. See, this is the pressure diagram. This is a temperature diagram. And this is the the density diagram. So given pressure, say 150 bar, given pressure, what if we decrease the temperature? Then density will be a gradually increase, along with this pipe, the pressure line, and we keep decreasing temperature. Okay? And density will increase, and then finally we reach the certain zone, which is the liquid. We write LH2, liquid LH2. This is the gas zone, compressed gas H2. Okay, CCH2 is a cryogenic compressed H2 is a still gas. So anyhow, under given the pressure, if we decrease the temperature, is always is a way to increase the density. So storage wise, it's always good to keep temperature low is the effective way to increase the density. And also, it is good to increase the pressure like this. So what does it mean? Well, meaning that for given temperature, isothermal case, if we increase the pressure, density will increase. So always better to lower the temperature, increase the pressure to increase the density. Okay, that would be nice to understand the in terms of storing hydrogen gas, but the keep lowering temperature is not easy task. The lower the temperature, you need extra energy. You may need a liquid nitrogen to cool down, or you need a sort of a heat pump. You need an additional equipment or energy to keep the lower the temperature. And also pressure. While pressure is not again easy to achieve, you need to have very big, very strong storage or compressor to keep the increase up. Okay. So first, what if we temperature as the room temperature? Room temperature is here. Room temperature. Let's keep the room temperature. Then H2 is always a gas. We only way we can increase the density is the pressure. Increase the pressure, and then reach the 700 bar here. Here. Okay. Oh, sorry. This is a room temperature. And then that time the density is the 40 gram per liter. Density is 40 gram to liter. This is a important number we need to remember. 40 gram to per liter. Imagine what's the size of a liter. A liter is the we are drinking water like the 1 liter or 2 liter of bottles, and then you can imagine how big the volume will be. Then each liter we can store 40 gram of the hydrogen. So to increase the more density, I'm sure that we can increase the pressure up and down, up and down. I mean, keep increasing. To do so, what do we need? We need a tank. Okay, we need a tank. So kind of a pressure tank. And also, if we like to have a lower the temperature, we can reach the liquid. This is a liquid. This is a liquid. Then, as you can see, very importantly, the pressure is no longer main point in pressure. See, look at this pressure line. Pressure goes always reaching this zone, right? Each pressure, you go to almost here, and here, and here, and here. So, in other words, if we reach the liquid by lowering temperature, we don't have to apply the pressure. So we don't need a high pressure tank. All we need to do is to keep the lower the temperature. So and then as you can see that this is the very typical liquid storage. As you can see that about the 70 gram per liter, and compared to a 40 gram per liter, let's extend this line. So 40, you can increase the 70 gram per liter by liquid hydrogen. It's not super high, but it is the almost the 70% up compared to a high pressure tank. But again, to keep the liquid, you have to keep the you need energy, you need a special insulation layers to keep this temperature. And the pressure tank, you don't have to lower the temperature, but you need to have a high pressure tank. Okay, so this is a two different extreme case. How you store the hydrogen. So hydrogen storage, you have a compressed or liquid. Okay, so chapter 5. hydrogen storage, compressed and liquid. Also, there can be some certification. Well, let's forget about the certification for a while. But this chapter covers hydrogen storage via compressed gas, 750 to 350 to 700, and liquid is again have to be less than minus 253. This is the phase changing temperature from a gas to a liquid. And then underground method and process certification procedures. And Hyundai Nexo, 6 kilogram per tank, Y6, 6 kilogram per tank. Well, this is not the not quite correct number. Actually, 2 kilogram per tank, since each tank is a 50 liter, 52 liter, and then we have a 3 tank. That's why we have a totally 6 kilogram per a vehicle. Okay, offers 560 kilometer ranges. This is a lot, very long ranges. Is as better than lithium-ion battery. Actually, there is a next generation of Nexo. We call Nexo 2 or SUV. Man, I forget the name. Yeah, all new Nexo. Okay, all new Nexo. As you can see that the very powerful, efficient hydrogen fuel cell system. Well, fuel cell system we didn't cover yet, but the fuel system will generate electricity from hydrogen gas, okay, delivering 200 horsepower, very high. Now, range is 700 kilometer, and new feature introduced 1,000 kilo, meaning that very lightweight. So this just released. Let's go to.
So what is the color you would go with if you want to choose Nexo? This white, that matte blue, or the first gray that we saw. But I had the last one saved on purpose. It is this amazing call of the day. I can actually feel something coming off of it. You guys can see it, right? I can smell it. This is the all new Nexo, and I
all new
have
Nexo
that review of the car with the concept, which was called Lithium, and that hasn't changed much, except for the exterior, the speed technology, the numbers and text and spec. I went over that video is carried over to this on Nexo. With a charge that only takes up to 5 minutes, you can travel over 700 kilometers. And
see, that's the one of the key points. By charging, charging time takes only less than 5 minutes, and then with the full charge, you can driver range can be up to 700 kilometer. You can go more than Busan from Seoul. So this is a new fascinating features, and also the vehicle has to be very light, mainly because they used a lot of composite, not just the composite means a bio resin composite or eco-friendly composite.
that is manufactured. Therefore, and we know, just like all EVs always have been, the driving range is actually always higher than the suggested range. Looking at the front look, 4
So we, as a Korean, Hyundai is the number one company which lead the industry of the fuel cell or hydrogen car all over the world. Look at how beautiful they are. Uh, well, personally, I like to purchase this car soon, within 2 months. Anyhow, the the there is of course the hydrogen tank. Let's see. Uh, okay, new Nexo, all new hydrogen Nexo features a state-of-art hydrogen storage system. As you can see that why we need a hydrogen storage system. And then now we know that we are using the room temperature, high pressure, not go into a liquid. There is some reason for that. So anyhow, they are using the seven tank configuration. Nexo is equipped with a 3 equal-sized high-pressure hydrogen tank strategically positioned beneath the boot floor and the rear seat. Okay, the total capacity 700 bar and so on, and tank construction type 4 carbon fiber composite material. The tank are both lightweight and robust, ensuring durability and safety under high pressure conditions. See, very light, and that's why we have to use the fiber reinforced composite and robust. Fuel cell, we will study more about the fuel cell later, but the fuel cell is the one which generates electricity from hydrogen. So this is hydrogen storages. Let's go for the little more. So well, ChatGPT doesn't calculate, but they are look for the all kinds of further information. Hydrogen tank configuration. I mean, there can be a lot of different types of hydrogen tank and storage, but since the vehicle is the one we can easily approach, that's why we are focusing on the all new Nexo at this point. Number of tank, okay, 3 equal-size high-pressure hydrogen tank, okay, and then total capacity 700 bar. See, 6.6 or 6.7 kilogram of hydrogen gas are stored. Why is that? Because each one, the volume is a 52 liter times the density. Density is the, as we just reviewed, the 4 here. You have a 40 gram per liter, right? 40 gram per liter. This is the density, 40 gram per liter. And each tank is the 52 liter times the 3. That's why we have about the 6 kilogram. Okay, 6 kilogram of hydrogen. Right, 6.6 precisely. And 2 tanks are located and beneath and etc. Tank construction safety, and there can be some while durability-wise, the temperature can be as low as -30. What does it mean? Well, if the pressure is dropped suddenly, the temperature will drop together. So that we have to understand that. And sometimes this tanker the temperature can go up to more than 80 degrees due to environment and etc. Refueling ranges and something. So this is the one. Well, this is a very typical hydrogen tank for the Nexo. This is a previous version, which was released 7 years ago. This is not the new one, but tank size is the same, actually. We could have used the bigger and larger tank, but importantly, we have to have a new certification procedures to produce this tank, which takes a lot of time. So at this point, we just use the same tank as before, but the performance-wise, it increased a lot due to lightweight, also high efficient fuel cell. So here, as you can see that, we have a 3 tank. Oops. I don't want to go here. There are 3 tank. This one, you can see more in detail. Nexo fuel cell, 3 tank. Well, as you can see, this 3 tank. You can see that from the bottom, and each one is a 52 liter, an identical tank size, and they are all located here. But the another famous hydrogen tank is the Mirai. Mirai is the Toyota, and their tank system is the little different from Hyundai. As you can see that there are only 2 tank and with a different size. I remember one is the about the 70 liter. Okay, I forgot the other one. So anyhow, there are two tank. Like this. Okay. So of course the tank size is different. That means that they have to produce 2 different tank. So maintenance wise, and qualification-wise, it takes more effort than producing one equal size. But there are, but efficiency-wise, I mean, volume-wise and space-wise, these can be more efficient. One thing we need to understand is that the Toyota, they produce the tank themselves, but Hyundai, they don't produce, they just design and, well, recently they got all kinds of filament winding machine, and all the engineer produce or learn how to design and how to produce the hydrogen tank using the winding machine. But the supplier is from outside. The company name called Iljin is the one applied right now. But sooner or later, the supply will be much more diverse. Many company should be able to produce. But again, the key point is that the certification is not easy to get a certification. That's why the right now it takes some time and effort. So this is the Mirai Toyota. Honestly, actually, the Mirai Toyota hydrogen tank storage system is advanced than the Hyundai. We can see that the Toyota has about the 2,000 patents on the hydrogen tank, whereas Hyundai has only less than 5. I remember. I might be wrong, but that much different in terms of R&D. But recently, I'm very gladly the Hyundai announced that they will focus more on hydrogen tank and hydrogen vehicles, meaning a lot of different types of hydrogen tank and etc. So who design, who manufacture? Well, all should be done by the mechanical engineers, and also a fuel cell system, and also as we cover the old electrolyzer is being designed, is being manufactured by the mechanical engineer. So understanding of first need to understand hydrogen gas and energy. But this trend is not just in Korea. Say China, well, Korea, and the India, but also Japan. We have a lot of research here. China, South Korea, India, and Japan are actively developing hydrogen storage technology and infrastructure. Infrastructure, what does it mean? We need to have a fuel stations. Again, this industry is a game-changing blue ocean area. You guys need to prepare yourself and then find a good opportunity in this area. Anyhow, these nations are investing heavily in research, development, and deployment of various hydrogen storage methods, including pressurized gas and cryogenic liquefaction and metal hydride, which we'll cover next week, and then to facilitate the storage and the distribution of hydrogen for fuel cell and other applications. And China is the largest producer of consumer of hydrogen globally. While technology-wise, Korea is leading, but China has the largest the consumer or bigger, much bigger the industry. They are exploring various hydrogen storage technology, including gas type and cryogenic storages. China is also looking into a potential of using chemical compound like ammonia. We have to also understand the other way of storing hydrogen using the ammonia gas or methanol, such as the natural gas. Okay, ammonia and methanol, sorry, and as a hydrogen carrier, and also CH4 methane as well. South Korea has a strong focus on hydrogen fuel cell electric vehicles and is investing and building a robust network because recently Hyundai has a big group focusing on R&D of hydrogen vehicles covering storage. They are exploring different different hydrogen storage method, including pressurized gas and so on. India, well, India, the market-wise, India can be bigger than China sooner or later. But technology-wise, they are very is at the level of a beginning. They are looking at various hydrogen storage methods, okay, and Japan, and so on. So well. Okay. One thing I like to emphasize of the design of this hydrogen tank is that for example, this is the hydrogen tank. With the end enclosure. So whatever we have designed, plus minus theta, which were considered in the pipe is the same, can be applied to a tank as well. See, this much area is the equivalent to the pipe. So pipe design can be applied to a tank with a enclosure. We call, and also we need to have a sort of here, and one side there is a hose where the hydrogen gas go in and out. So anyhow, a lot of the new technologies being developed in fuel cell, and this is a way to reach the net zero, no CO2 emission society. And with this, we go into a fuel cell, and which would generate electricity, and this go to a motor. So we need to understand the tank, we need to understand fuel cell, we need to understand motor. Motor is the actuating system, which does, all kinds of movement. Can be well used the robot, motor, all kinds of motor here. And then this motor also can be well used in the robot system, and etc. So understanding robot, man, is so important, and fuel cell. Now actually just the water H2O through electrolyzer. See, we give energy, we get the H2. This the H2 is stored here, and then this is the H2, and then we generate voltages, and we get the motor. And then we get nothing but the H2O back. So H2O, starting from H2O, we get the H2O. So H2O, to get the H2, we put a lot of energy. Actually, we put the energy in, right? We get the energy in to get the H2. So this is the energy in. Actually, here we get the energy out in terms of running the motor. So there will be some energy in and energy out. This could be a total efficiency of this fuel system. So all the energy can come from renewable energy. So which will convert H2O into H2, and so we get all the energy in there. So that's why we often call H2 as the energy carrier. H2. We put the energy into H2, and H2 can be stored, distribute, and go into fuel cell and giving us the energy back. We giving the power to the motor, and which will give us the transport working as a transportation. And the output is nothing but the H2O. That was the original H2O. So understanding whole procedure, I kept emphasizing this one, and by now I'm sure you understand what it means. So again, today topic is the storage tank, how to design that. So rather than go into a detailed design, while that can be done, don't worry. There is a lot of technology and methodology and materials and so on and so on. But the point here is that we need to understand the whole system and why we need these types of gas storage rather than liquid type, and the all kinds of aspects of the storage system. So okay, this is all the topic I like to cover today as a hydrogen storage system, mainly introducing the all new Nexo. Well, again, as I said, I hope to have a chance to show this new Nexo vehicle to you guys. But anyhow, you can go to I was told that there is some exhibition which shows the where you can take a look the new all new Nexo. I hope you can find out. So anyhow, thank you so much. This is the topic I like to cover. The class is dismissed. Okay, if you have questions, please upload to Kato. Thank you.